66 million years ago, a single asteroid impact completely wiped out the dinosaur species. Earth sits in a chaotic solar system, and a similar strike today would instantly erase human civilization. To guarantee our long-term survival, we have to establish a presence on more than one planet. Today, aerospace organizations are actively building the hardware to make that happen. Visionaries like Elon Musk have explicitly set a target of establishing a self-sustaining city of 1 million people on the surface of Mars. Reaching that scale requires lifting massive amounts of cargo. The Starship rocket is designed to carry a 150 metric ton payload to the Martian surface, a capacity that dwarfs any previous launch system. But orbital mechanics dictate exactly when we can launch. Earth and Mars rotate at different speeds, meaning the optimal launch window only aligns every 26 months. A single trip takes 7 to 9 months, making an emergency rescue or an immediate return mathematically impossible. If a critical system fails upon arrival, the crew is entirely on their own. Yet surviving the cold, isolated vacuum of deep space is ultimately just the commute. The true challenge of colonization begins after touchdown. Mars presents a specific set of physical conditions that dismantle human biology the moment an airlock opens. The first thing you notice on the surface is an endless, rusted desert. The soil is rich in iron oxide, the exact same chemical compound that causes metal to rust on Earth, giving the entire landscape a permanent, heavy red hue. But the air above that soil is drastically different. The Martian atmosphere is incredibly thin, holding only 1% of the density of the atmosphere we breathe on Earth. That thin air is composed of 95% carbon dioxide. If you took off your helmet, the lack of pressure and toxic gas would cause you to lose consciousness in roughly 15 seconds. Within 2 minutes, you would be dead. Because the atmosphere lacks density, it is completely incapable of trapping heat from the sun. The moment the sun sets, any surface warmth instantly escapes back into the vacuum of space. This creates a constant, deep freeze. The average surface temperature sits at -60 degrees Celsius, and during the winter at the poles, it drops down to -125 degrees. That is cold enough to freeze human blood. Stepping onto the Martian dirt without a heavily insulated, perfectly pressurized spacesuit results in a total biological failure by either freezing or suffocation. Earth has an active magnetic field that safely deflects lethal solar flares. Mars lacks this magnetosphere, meaning radioactive particles crash directly into the surface. A single year on Mars equals 8 years of Earth-level radiation, severely spiking the probability of fatal cancers. This constant bombardment means the classic science fiction vision of building transparent glass domes on the Martian surface is a physical impossibility. The glass would offer zero meaningful protection from the cosmic rays. To survive, engineers will rely on in-situ resource utilization, using local Martian materials instead of shipping everything from Earth. Fleets of autonomous robots could use the iron-rich soil to 3D print thick, heavy construction materials before humans ever arrive. The most effective way to block radiation and stabilize extreme temperature swings is to use the planet itself as insulation. Colonists will have to dig down and build their permanent habitats several meters underneath the Martian dirt. Feeding those colonists poses another hurdle. The Martian soil contains high levels of perchlorates, toxic chemical compounds that make the dirt lethal to plant life. Agriculture will require deep underground hydroponic systems, relying on artificial LED lighting and water extracted from subsurface ice. Surviving a new sun requires a total retreat from the surface. A Martian colony will be a sprawling subterranean network, entirely dependent on automated life support systems to keep the void at bay. We can generate our own oxygen, insulate against the cold, and bury ourselves from the radiation. But there is exactly one basic planetary metric we do not have the technology to fake or engineer away. That metric is gravity. The physical mass of Mars generates only 38% of the gravitational pull we experience on Earth. Look at this anatomical model comparing human development. On Earth, we evolve under 1g, or normal Earth gravity, which forces our bones and muscles to grow dense and compact. Extended time in Mars's 0.38 g, roughly a third of our normal gravity, causes severe degradation of muscle mass and a dangerous drop in bone density. The first generation of children born inside those underground colonies will have a completely different developmental cycle. Having never experienced the heavy pull of Earth, their bodies will naturally grow taller, with elongated limbs and far lighter bone structures. Over multiple generations, the physical differences will compound. The strict environmental pressures of low gravity will force human biology down an entirely separate evolutionary path. If this sounds distantly futuristic, consider our own aerospace timeline. In 1903, the Wright brothers managed a brief, fragile flight across a beach. Just 66 years later, humans were walking on the moon. Technological capability compounds rapidly. The push toward Mars is an engineering leap that results in a permanent divergence in our species. By adapting to the gravity and radiation of an alien world, the descendants of Earth will cease to be Earthlings. They will be the first true Martians.